I'm sharing my screen. What topic last class we discussed? Anyone remember? What was the
Stress strain curve.
okay, we discussed this part. My screen is visible.
Yes, ma'am.
We discussed this part. We discussed this curve, all the parts of this curve, linear, elastic region, perfectly plastic, yielding, strain hardening, necking. We discussed this part.
Yeah, yeah.
Then maybe today we have to start the material properties, right? Are you guys familiar with this part? The whole part, this in stress, strain hardening. How many students are there? 29. Only one responding. What about others? Shall I discuss this graph once more or shall I move to the next topic? Type in the chat box yes or no. Shall
Yes, ma'am.
okay, Hokato, okay, fine. Let's others talk. Speak, sorry. Next topic, okay. Perfect. Abrisha, what? Yes, ma'am. Just reply next topic or shall I explain this one once more? Next topic.
Once more, ma'am.
Once more, okay. Majority will be win. Look, don't write lol and all. Just next topic. I have asked once more or next topic. Okay, once more. Once more. Okay. So majority they have said once more. 31 participants. So I'll without any late I'll start the class. Okay. So from the last class we discussed this was a basic typical stress strain graph which we used to get from this tension test. Now we'll discuss the parts of this graph. And please stop me if my screen is not visible. Okay. Let me change the color. Okay. Blue will be perfect. Okay. So this in x-axis we have strain and in y-axis we have stress. Okay. For different material you will have a stress strain diagram. Suppose aluminium, copper, steel, rubber. You will have stress strain diagram for every material. Okay. And all the components will be same in the curve, but the shape can be a little bit different from this curve. I have taken this stress strain diagram for suppose steel. Okay, every member will phase go through a elastic region, a plastic region, there will be a strain hardening region, and there will be a necking. Okay, so we'll start with the linear part. See this curve from 0, we are stretching. Suppose I'm taking a spring. Okay, I'm stretching this spring and it gets reformed up to a certain limit, which is till this point your stress, if I'm representing by sigma, is directly proportional to your strain. In this region your stress is directly proportional to your strain. Okay, so from this is the linear part of the curve. This is the linear. See, linear, it is directly proportional to stress. Whatever we are getting stress will get a strain. Whatever we are getting stress, it will give a strain. So this region is linear region, and the point beside this is your proportional limit. Why proportional limit? This stress is directly proportional to your strain. So that is the proportional limit of the curve. Okay, now again I stretch this okay, one more point. Till this point, uh, till this point we are getting a structure undeformed. Suppose if I'm stretching, after if I leave the force, it will regain its original shape. Okay, we are stretching a rubber and we are leaving that rubber, then it will, suppose after stretching it will stretch out, and when I leave the force and it will come back to its original position. So this is the basically linear part of the region. Next, again see the shape of the curve little bit changes, And in this part, this is also elastic region. Till this point, if we give a if we stretch a rubber, it will come back to its original position. But here, proportional limit will not occur. In this area, this is the linear part. This part is little bit non-linear part. This is little bit non-linear part. Okay, but till this point, your structure or your member or your material will come back to its original position. Okay, if you give a stress, if you give a force, it will come back to its original position. Okay, and the point from this is yield stress. Yield stress means from this point your structure will start getting deformations. After this point, if you give a stress, it will get elongated. It won't come back to its original position. Okay, this is the stress when your deformation starts. That's why it is called yield stress. So this region is your elastic region. Okay, in elastic region itself we have two parts. One is linear region and the small part is, earlier we have studied na, a graph will have a linear region and non-linear region. This graph we have studied na, this is the linear region, this is the non-linear region. So in this curve, this is the linear region, and in elastic region we have small part of non-linear region. Hope this part is clear. Now what happens if you give a stretch? Suppose this is a spring. I have given a force and it crosses its elastic region. Now whatever I give a stretch, it will get deformed. Suppose I have stretched, it will get elongated. Again I give a stress, again it will get more elongated. So like this region, after yield stress, whatever you give a stress on that member, it will get elongated. So your member was in elastic region for some time. After yield stress, your member comes to a plastic region. That means if you give a stress, it will get elongated. It will get deformation. It won't come back to its original position. So this part is nothing but perfectly plastic yielding. Now your section is in plastic section. Okay. Now after this point, your structure member will get a high stress in the upward direction, and this stress is called as ultimate stress. This is the point where your structure can take the highest load. You can apply the structure the highest load. After that it won't take any stress. So this portion is nothing but strain hardening. We'll discuss strain hardening in next slides. So this is this portion when your stress becomes high, it reaches its peak. That portion is known as strain hardening, and that stress is also called as ultimate stress. The highest stress a body can take. Okay, then after that your structure starts fracture, it will get deformed. Okay, so this portion is called as necking. Your structure fails at this point. Now see, now here stress is your nominal stress. I have discussed nominal stress is nothing but normal force by original area, right? Now this is when you calculate nominal stress, which is engineering stress. We use engineering stress in our structures. That's why this area is more, so this stress will be less. That's why it comes down. But if you talk about true stress, that was normal force by your deformed area, right? Deformed area means suppose you have taken this is a rubber. Suppose I'm taking a stretched rubber. If you stretched out, your rubber will becomes this much, right? Your diameter or your width becomes less. So earlier the area was your earlier area was A naught, and this area will be your A. Remember or not? Or should I go to the review part? This one. This one. Which one? True stress will be more or
Yes, remember.
yeah, true stress will be more or nominal stress? Nominal stress, we are taking the initial area before deflection, the original area. But true stress, we are taking the area which we get after the elongation. When you elongated it, your area becomes less. So that's why true stress goes in upward direction. Okay. So if we are taking out true stress, the curve will go in upward direction. But if we are generally we take engineering stress or nominal stress, that's why it is going downward. So this is the typical stress strain diagram of a material. Okay, these parts will be common to all the curves, but shape can be different. Okay, hope this part is clear. Now let's move to the properties we can take from this stress strain curve. So let's start with stiffness. What a stiffness is. So what do you understand by the stiffness? What the word suggests to you? Anyone? What this stiffness means to you? What does words uh, make you understand stiffness?
Ma'am,
See,
toughness of the material.
yes, good, good, very good. Hardness, yes. See, one more thing I want to share with you, that your class response will be noted. You have class impression marks. Okay, so we are taking a live class so that you can interact with us. So I'll note down who is interacting with me. If you have any network connection, type in the chat box, but interact. Okay, okay. So let's start. Yes, hardness. You can say hardness also. How hard it is. Okay. So this hardness is represented by nothing but your Young's modulus. That is E, right? And what we got E? We got E is nothing but slope of this curve. So more the E value, more will be the stiffness. More E, you can write more E value, more will be the stiffness. Less E value, less will be the stiffness. Okay. Suppose rubber will have more stiffness or steel. Rubber will have more stiffness or steel. In generally, rubber will be more hard or steel. Steel. Okay. Yes, yes. Steel. So the slope of this curve will be more. So suppose you have been given a two curve. You have to find which one is more steep. Suppose you don't know the material name. You have been just given a E value. Okay. The curve which have more E value, that will be the E means the material which will have more Young's modulus, that will have more stiffness. Okay. Suppose you have been given a one more curve. So you have to find the E value of this curve. How will you find E? We'll come to the part. Then you find E value of this. Then you'll compare. Then you'll understand which one is more steep. Okay. So more the slope, more the E value, more will be the steepness. Okay. Now let's come to the Hooke's law. Hooke's law. This is very important point, that it is valid for linear elastic region, but linear. So we have in elastic region we have two sections. One is linear, another is non-linear. And Hooke's law is valid for your only linear region. Okay. Why? Because you'll understand from the law itself. Hooke's law states that your your stress is directly proportional to your Young's modulus. This is sigma. This is, oh, sorry, I draw E part. Let me note once again. So Hooke's law states that your sigma is directly proportional to your strain. Strain is your epsilon, right? Now you can remove this directly proportional by a constant. What is this constant? It is nothing but E, which is Young's modulus. So understood? Your Hooke's law states that, see, Hooke's law is a very common question you will find till your end semester viva. What is Hooke's law? States that what is Hooke's law. So just not mug up. This is easy. Stress is directly proportional to strain, and that directly proportional is removed by nothing but Young's modulus. So how will you find the Young's modulus? You should have a stress value, you should have a strain value. Okay. Now who will tell me what will be the unit of E? What will be the unit of E? Anyone? What will be the unit of E? or it will be unitless?
No unit, ma'am.
No unit. Okay. Anyone answer? Anyone?
Unitless.
Okay. Okay. Noted. Roll number 1. What about others? It will be unitless or unit? Anyone? No. Okay.
Unitless.
Unitless. Okay. Just see now. Your Young's modulus is nothing but stress is equals to E by epsilon, right? So Young's modulus can also be written as stress by strain. Stress has a unit of, suppose, Newton per mm square, right? Strain has no unit, zero unit, no unit. Now tell me what will be the unit of E? No unit. Now tell me what will be the unit of, yes. So the unit of N will be Newton per mm.
Newton upon
Yes,
meter square.
yes, yes, yes. So E will have the unit of sigma itself, that is stress, because stress doesn't have any unit. Strain has a stress has unit of this much. This doesn't have any unit, so E will have, E is directly proportional. E will have the unit of stress. Clear? So this stiffness part is clear. You calculate, you find out the E value, and the material which have more E value, it will be more stiff or hard. Okay. Then let's move to this another properties. Then we have strength. Strength is represented by how much stress it can take. Okay. And from this curve we can find out capacity for high stress or ultimate stress. So the curve which will have ultimate stress, that will have high strength. Suppose I'm curved. My curve is very bad. Let me draw once again. Suppose I have one more curve like this. Okay, its ultimate stress is at this point. So this is a curve of, suppose, aluminium. I have drawn a stress strain curve for aluminium, and this one is for steel. Steel has a ultimate stress of at this point, and aluminium has ultimate stress at this point. So which one will be more strength? The one which have more ultimate stress. Okay. Strength is nothing but capacity for how much stress it can take. Next, move to the topic property. Next, move to the property of toughness. So toughness can be represented here. Capacity for energy absorption. How much energy can it absorb will represented by your toughness. Okay. Now in this curve, you can calculate toughness area under stress strain curve. So this whole area, you have to find out the whole area. Then the curve which will have more area, it will have more toughness. Okay, you will understand how to calculate this property in the, ma'am, I can't hear your voice. Is it similar with all of you? Roll number 29, my voice is clear. Hello, hello, am I audible? Rohit?
Yes, ma'am.
Yes, ma'am.
Okay, I
We
can.
can hear.
Okay, okay. Maybe Rohit, you have some network issue. Please check. Okay, so your toughness will depend upon. Today I made sure that I will be visible in a. So I'm top of my terrace. Beyond that I can't go anywhere. Okay. Then let's move to the next topic. Resilience. Still, if you face any problem, if you don't see my cursor, let me know. Okay. Okay. Next is resilience. Resilience is nothing but how elastically it will comes back. Capacity of deforming elastically. How much and you can find this resilience property area under elastic region. So this you have to find the area of this elastic region of different curves and compare. Okay. So resilience is nothing but how easily it will bounce back. When you stretch, is it how fast it will come back. Okay. So this area will depicts your resilience property. Next is your Ductility. Ductility, you know, capacity. This you have got this word, I guess, ductility and brittleness. So ductility will be capacity for high deformation. How much we can stretch it out, how much strain it will give, will pull it out, how it will elongate it. So from this curve, it will be the area under this. How long is the curve? Okay, ductility will represent how long is the curve. Longer the curve, more will be the ductility. Shorter the curve, shorter will be ductility, and that shorter will represented by your brittleness. Okay, low capacity for deformation and straw. Longer will be the curve, longer will be the ductility. So your ductility metal, you can take example of like what will be, give me an example of ductile material. Any ductile material, give me an example. Anyone can give me example of ductile material? Brittle material?
Rubber band.
Copper.
What? Not audible.
Rubber band.
Yes.
Ma'am, copper.
Yes. So and brittle material, you can take an example of concrete, right? It will break glass. So that is how it is. Hope. So we saw stiffness, strength, toughness, resilience, ductility, then brittleness. So I want you to go through this question. In this worksheet, you have been given a strain values in the x direction. You have been given a stress in this direction, and you have been given a two curve. One is for, forget about this complex name, just see, you have been given three materials: steel, aluminum, and magnesium. Three stress strain curves are given to you. Okay, and you have to find first modulus of elasticity for steel. How will you find the elasticity for steel? How will you find the modulus of elasticity? How will you solve this question number 1? Modulus of elasticity for steel. Let me show you this diagram. How will you find the modulus of elasticity for steel? Steel is this one. Steel is this curve. How will you find the E value? No idea? Okay, let me share.
Stress
See,
by strain, ma'am.
yes, from this,
250.
yes. So this is our curve. We have to find E for steel. So our E is nothing but stress by strain, right? So what is the stress from the curve? This is 250 is our stress. 250 is our stress. And what is our strain? If you draw this in graph, you will get this value, okay? So if I point out, so this is my strain, which is 0.00125. So how much I'll get? How much I'll get? Calculate. It will be 250 divided by 0.00125. So it will be 2 lakh, right? What answer? Let me allow 2 lakh. Got 2 lakh? And see the unit here.
Yes, ma'am.
Here unit is MPa. So our answer will be 2 lakh MPa. And you can convert also in GPA also. So it will be 200 approx GPA. Okay. Then what I have been asked? I'll show the answer also. Don't worry. Then I have been asked to find the ultimate strength of steel. This is our steel ultimate strength. I explained you ultimate strength will be represented by your ultimate stress value, right? So what is the ultimate stress of this steel? This one. This is the peak point. After this curve is deflecting, right? So this will be ultimate stress point. If I point it out in a y direction, what I get? 400 NPa. So your ultimate strength, this ultimate strength will be for Ultimate strength of steel will be nothing but 400 MPa. Understood? Clear? Next, I have been asked to find ultimate strength of aluminium. Which one is our aluminium? This one. This one is our aluminium. So from this point it is necking down. So this point will be your ultimate stress. So I got 310 as my ultimate strength for aluminium. Next question is, I have been asked to find proportional limit of common magnesium alloy. So proportional limit was which one? The point your curve starts, the point where your straight part of the curve ends, right? This is your proportional limit. So I have been asked to find the proportional limit of alloy, magnesium. So this is the part, from this point your curve starts bending. So this will be your ultimate proportional limit, which is 125. Got it? Clear? Next, I have been asked to find the yield stress of A36 steel. A36 steel, that is yield stress. So yield stress is nothing but the point where it shows deformation. So this will be also 250 MPa. Till question number 1 to 5, it is clear or not? Am I audible?
Yes, ma'am.
Yes, ma'am.
From question number 1 to 5, it is clear?
Yes, ma'am.
Yes, ma'am.
Okay. Next, move to which of these material is the strongest? Aluminium and magnesium. Now you respond. Which one will be strongest? Aluminium or magnesium?
Aluminium.
Aluminium. What about others?
Ma'am, aluminium.
Okay. Okay. Why?
Mm,
Ma'am, because it can resist the
because
highest
it
amount
has
of stress.
It can resist?
The highest amount of stress.
Okay. Okay. Let's answer this. Which one is the most ductile material among these three? Among these three, which one is the most ductile? For ductile, we have capacity of high deformation strength. So which one will be more ductile? Steel, aluminum or magnesium?
magnesium.
Magnesium. Others?
Magnesium.
Yes, yes. Magnesium, magnesium. I got the answer. Okay, okay. Perfect. Good. Now you are interacting. And which one will be most brittle? Which one will be most
Mm,
brittle?
aluminium.
Aluminum.
Aluminium.
Okay, good. Next, which material is the stiffest?
Steel.
Yes, it is steel. So this is the answer.
Steel.
Yes, yes, yes. Good. Very good.
Yeah.
Yes, good. So this is the answer. Okay. We got modulus of elasticity, stress by strain to 2 lakh MPa when we have converted into 200 GPa. Then ultimate strength was steel. That was the ultimate stress 400 MPa. This is 400 MPa. Again for aluminium, this was the aluminium yield stress. The highest stress was 310. Sorry, so 310 MPa. Then proportional limit of magnesium. Proportional limit of magnesium was the point where your curve starts. It leaves the straight part. So this is the 125. So this is the answer 125. Then yield stress of steel. Yield stress of steel where it starts yielding. So this is 250. So this is the answer. Hope this worksheet is clear to you all. Now let's move to the next. Okay. Basically, I have discussed three typical graphs, right? I've discussed with you three typical graphs. Just wait a minute. Okay. So we have three typical materials. One is steel, another is your aluminum, and another we have we saw magnesium. Okay, so these different materials, just wait a minute. Okay, okay. So we have we saw a typical stress strain diagram of these three materials, right? One we have considered as steel, another aluminum, and the last one we have saw for magnesium, right? And the steel, where the steel is used, it is used in machine parts, shafts, right? And it is a ductile material, and it has a lot of strain before it allows for a lot of strain before it fractures. This steel, before it fractures, it have a lot of strain in this in this it has gone many strain before it get actual fractures. Okay, the other material is aluminum. One of it has been typically used in past for aircraft frames. Although now we are seeing a lot more composites in aircraft frames, the strength to weight ratio, the main part, okay, the main part is the strength to weight ratio in aluminum is better than steel. Although steel is stronger, so that strength to weight ratio is a reason they used in aircraft, because you can get a lot of strength for less weight. That's what you want to have in an aircraft type application. Okay, now you are starting actually to see aluminum used in cars and pickup these days. And then finally, the third material we have magnesium. It's a low density metal, about two-thirds that of aluminum. What magnesium is what? It's a low density metal, about two-thirds that of aluminum, and it has a good corrosion resistance. It has good high temperature properties, and it is also used in electronic applications and some other special applications. So we have talked the basic what where these curves, where these materials are used nowadays. Now let's move to the main part, yield stress. Okay, what is yield stress? As I have discussed earlier, that this is a stress from where your body starts deforming. It will show your permanent deformation, or you, and you can also describe it as a lower stress that produce permanent deformation. After this point, you will get a permanent deformation in the body or in the structure. But see, this is the steel curve. You have get perfect yield stress. The yield stress is perfectly defined in this in steel material. But if you compare with magnesium and aluminum, your yield stress is not defined perfectly, right? So it is difficult to identify these yield stress in these curves. So what you have been given an option that if the point of yielding is difficult to identify, you can typically take 0.2% offset yield stress. Okay, you can take 0.2% of offset yield stress. That means wherever is the 0.2 strain, you draw parallel to that parallel to this, you draw a line on that curve. The point where it intersects, take that value on the stress. That will be your nothing but that value will be nothing but your offset yield stress. Clear? In some curves, you won't get a well defined yield stress point. So what you have to do, you have to take 0.2% offset yield stress for that curve. Clear? Next, write down this question actually, or you can take a screenshot of this. You can take a screenshot of this. You have to find what is the approximate 0.2% offset yield stress of Aluminium. This is the curve. You have to find what will be the 0.2% offset yield stress for this aluminium. Can you do it now and tell me the answer? Or you can say the answer now.
Ma'am,
Yes. Yes.
what does 0.2 means here?
Strain. 0.2 means this strain. This strain. 0.2% or 0.02 strain. At this point, draw a parallel line to this. Draw a line parallel to a curve, and the point where it's intersect, take a value on the stress value. That will be your 0.2% offset yield stress. So for this, you have to find for aluminium.
Okay, ma'am.
Can you say that just by looking at the curve? It's okay. Try a guess nearer to the value, exact value. Anyone?
110?
110. If this is aluminium, right? If this is 1, 2,
110 or 120?
if I draw a parallel line to this curve, it will reach around here. How come 110?
300, ma'am.
Huh?
300,
Okay. Anyone?
300.
300. 300.
Yes. Marina, yes. How much? Yes. So answer is 310. If you find yes, yes. Jashila, yes. Correct. So the answer is approximately 310. Okay. Aluminium. See the word aluminium. So we have to find for this curve aluminium. So if I take 0.2% here, if I draw a parallel line here, if I represent with this, so it will come around here 310. Okay. Now let's move. Sorry. Sorry. So let's move to the part strain hardening and permanent strain. So we discussed this part, which will be the which 0.2% offset yield stress will be your yield stress. Now let's move to the strain hardening, which is also called as work hardening. Okay, it is nothing but increase. Just give me a second. Okay, am I audible? Am I audible? Hello.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Okay. Now I want to look about something called strain hardening. Okay. So what is strain hardening? It's an ability to increase the yield strength. Okay. It is an ability. Listen carefully. It is an ability to increase the. It is a. Where is my note? It is an ability to increase the. It is an ability to increase the yield strength or the strengthening of the material by this permanent or plastic deformation that takes place. Okay, I'm repeating, it is an ability to increase the yield strength or the strengthening of the material by this permanent or plastic deformation that takes place. And this permanent or plastic deformation that takes place, we call the permanent set or residual strain. Okay, so here is the graph of the concept of strain hardening and permanent set. Suppose we have a material and we can load it up to a point 1. We have a material, we are loading it up to a point 1 here, where it starts to yield. Okay, at this point it starts to yield, and let's go up to some point 2 here. where we will unload it. Will release this force. What we did, we stretched our member to a point 1, where it starts yielding. Okay, it's showing deformation, and then we move to a point 2. After reaching 2, we unloaded the member. Okay, then we had some plastic deformation. When we unload the member, we'll have that it changes from its original dimension. It changes to another dimension. Okay, so we have some residual strain. Okay, we after unloading we had some plastic deformation, so we have some residual strain or permanences. And then we see, if we would load it again, we wouldn't start to yield until we got to point 2. Understood? We have taken our member, we have stretched it out. Okay, it starts yielding at point 1. Then we again move to a point 2. Right? After reaching 2, we have removed the stretch, and we saw that our body deformed already. Okay, our body deformed already. Now again, when we load, it doesn't yield at 1. Okay, it crosses 1, and then at from the 2 point it starts yielding. So what we did, we have increased the strength of the material. Okay, what we have increased the yield stress. Earlier the yield stress was 1 at one point, at the point 1, but now your yield stress point has shifted to a point of 2. So that is the phenomenon of strain hardening. Clear? So we have some strain hardening because the yield stress now is higher than it was the first time we went up to the curve. So this concept of so this is the concept of work hardening, or you can say strain hardening or residual strength. Clear? Okay. Then let's define and calculate Poissons ratio. So basically Poissons ratio is for your uniaxial loading. We are seeing the Poissons ratio for uniaxial stress and strain. So what actually happens when we pulled out of body? Earlier the body was in this direction. The dimension of the body was like this. When we stretched out, your body became do one thing. The meeting will end in 5 minutes, so do one thing and write your roll number in the chat box. Please write your roll number in the chat box for the time being. This meeting will end. Hope all of you have written their roll number in the chat box. Only 31 member. What about others? They are not aware of class. At the end of the semester, they will cry that we didn't get any attendance. Everyone wrote their roll number, then I'll continue with the class. If the meeting ends, then we'll continue in the next class. Okay, let me quickly. Screen is visible? Screen is visible?
No, ma'am.
No.
Yeah.
Okay. So what happens actually?
Visible now. It's visible now.
Okay. So what happens actually when you pulled out, your diameter becomes less. Okay. This is the lateral dimension. And then when you compress, then your diameter becomes increased. Earlier your dimension was this, and now your dimension has become like this. Okay, so your Poissons ratio is nothing but it's a ratio of lateral strain by longitudinal strain. Now what is lateral strain? Lateral strains means your change in dimension in lateral direction by its original dimension, original width. Okay, original width by how much change in the lateral direction. And longitudinal strain is change in direction, change in the length, change in length by its original length. So your Poissons ratio is your uh, mm, lateral strain by longitudinal strain, and sign is given as negative. Okay, and we assume that for homogeneous material is said that same material throughout. Throughout the section, this material will be same. Okay, and isotropic is generally said as same material properties in all direction. Whether you go in X, Y, and Z, your material property will same in all the direction.